vLLM community. My name is Sasha Zelanovic, and I am a Senior Technical Marketing Manager at Red Hat AI. I'm joined here by Michael Goin, who is a vLLM core maintainer, also from the Red Hat AI team, as well as Christoph, our friend from Intel, who is based in Poland. It's pretty late for Christoph, but he'll be here telling us how to run GenAI workloads on vLLM on Intel CPUs. I know this has been a age-old question about running AI or GenAI on CPU, so I'm really excited about this talk. I know many other people are as well. So Christoph will give you a chance to introduce yourself once your time comes. We are very happy to have you here. So welcome to our 50th office hours. I've been waiting for this moment. 50 is a nice round number. It's been a year and a half that we've been doing this, so it's super nice to see that we continued on this quest and that there are many more office hours to come. If you're new to these office hours, we do meet every other week on Thursday at 2 p.m. Sometimes we do skip, but we do tend to make those sessions up. We do record all of the sessions. Let me actually go to the next slide. We do record all of the sessions. You can find them on YouTube. All of the slides from all of the sessions are linked in the YouTube description, so you can always find them there if you can't make it here. We do stream these sessions also on X Live and on YouTube Live. So if you ever want to join in those channels, that's always also welcome. So today, as I said, we're talking about vLLM on CPUs. Pumped about that session. In 2 weeks, we'll have a pretty wholesome speculators update. There's been a new that's gone into the speculators library. We've also released new techniques, new models, speculative coding models. So Deepika and team from Red Hat are going to join us in 2 weeks and share all of that with you. I know speculative coding is a hot topic, so excited about that one as well. And then on June 25th, in a month or so, in 30 days or so, Christopher Newland, who is our chief AI architect at Red Hat, he'll join and talk about the vLLM semantic router, one of his favorite projects. He'll tell you all about what this is and also showing some actual enterprise use cases. I saw Christopher deliver this talk a few days ago at a meetup we had in Boston. It was very interesting how banks, for example, are using semantic router to keep private information local while using foundational models or the bigger closed source models for more tasks that don't require privacy. That was just one use case. I'm pretty excited about Christopher's talk. Michael, do you want to quickly share what's new in the vLLM project update here, and then we can go to meetups?
Yeah, for sure. Good to see everyone again. Thank you all for being here. I didn't realize myself that this is the 50th one, but it's cool to have done so many of these. Today we have like a pretty good bunch of blogs on the vLLM blog that I'm going to walk you through. Some turbo quant, KV cache quantization results, RL for like omni-modality models. Elastic EP is finally shipped and ready to talk about, and of course the latest 0.21 release on vLLM. So yeah, we'll dive into that in a bit.
Awesome, thank you, Michael. And then just quickly before I pass it over to Michael for a detailed breakthrough of all of these, or not breakthrough, whatever the words I'm looking for, detailed look into all of these things, I just want to quickly mention 2 upcoming meetups. So we'll be in London on June 10th in about 2 weeks or so. Really excited about this one. We'll be talking about both vLLM and LLMD. We have a very nice sponsor roster. So Red Hat, obviously, Stellia AI, who is a local company to London, as well as NVIDIA will be there. So there's a link to register, and Michael has shared the deck that you can click into it, or just send me a Slack or a message and I can send you a direct link. And then a week after that, Michael will be continuing from London to Istanbul, where we'll be on June 17th. That one is shaping quite nicely. We're expecting about 300 people there. And what's exciting about Istanbul, for me at least, is that we have 14 Red Hat customers from Turkey have vLLM deployed. So we'll be telling a lot of those deployment stories, which is slightly different than most of the other meetups. So that's pretty exciting. So with that said, Michael, I'm going to pass it over to you to go into the vLLM updates.
Cool. Thanks a lot, Sasha. To kick us off, I want to make sure you're familiar with vLLM if you're not already. It's the open source standard for high throughput, memory efficient, open source, inference serving of large language models. It's the most popular, production LLM serving engine. over 80K GitHub stars over the past 3 years, and we got 2,000 PRs a month submitted. We are able to merge about half of those, surprisingly. So we're kind of keeping up in terms of commit rate, but yeah, it's a very active project with thousands of contributors from dozens of major companies and academic institutions. Working on it for different hardware backends. Obviously, Intel's here to talk about their great CPU work and optimizations that they develop on vLLM. vLLM is ultimately successful because it is that software layer that defines the sort of abstract operations to run the latest state-of-the-art models of the year, of the week. Allowing for a pluggable interface for hardware backends to get great performance on those various complex model definitions. vLLM is highlighted by its easy to use Python-based library. It's just a pip install away, and you can get started on vLLM Serve on your hardware. It supports hundreds of different unique model architectures with different types of device parallelism. So running those models, with tensor parallelism or pipeline parallelism sharded on a single node of accelerators, or even doing, internode, acceleration, even hosting, large disaggregated pre-filled decode deployments for like cluster scale, DeepSeek deployments. We're able to replicate a lot of those things and build those with distributed inference libraries like LMD or Dynamo. vLLM goes beyond just the inference engine itself. It's ultimately a larger vLLM project, part of the PyTorch Foundation. And we have projects like vLLM Omni, Speculators, GuideLLM, vLLM Semantic Router, like Sasha mentioned before, and many more. So definitely hope you are active in the GitHub community around it, and also the vLLM Slack, where we're very active, and it's great to answer questions and get development there. So after that brief introduction, I'm going to go over some of the blogs and releases we've had over the past 2 weeks since the last office hours. There was this interesting blog from the NVIDIA model development team on their latest Omni model. This expands it from just image input to video and audio input compared to the previous Nematron 3 models. And there's some pretty interesting insights there on how they implemented this efficiently from the model architecture perspective, if you're interested in those things. Especially in terms of efficient video sampling, I think was covered quite well. And they compare against Qwen 3 Omni on Blackwell GPUs and show great sort of efficiency gains. And of course, it's a pretty capable model that's interesting for enterprise usage as well, because it's permissively licensed. So yeah, check that out if you're interested in those features. Another really kind of big blog in the process is a collaboration between vLLM and Mooncake, particularly Mooncake Store, to use Mooncake as a distributed KV cache pool to ultimately share KV cache between prefill and decode instances of vLLM, and driving better prefix cache rates. So obviously improving your time to first token, greatly improving throughput as a result, because you can spend more time doing your decodes and need less space inefficiency. And yeah, there's, as you can tell from here, there's some great GIFs and architecture diagrams for how this is done. Of course, the performance is great to see, but I really like as well some of these breakdowns into why these KV cache management and prefix cache hit rates are so important in this sort of anatomy of an agentic trace, which really kind of steps you through the timescales between it's not just sort of multi-turn conversations are happening 1 second after another. Sometimes the agent needs to make a tool call or run a test job that needs to run for a minute or 10 minutes. It's really important that we don't lose that KV cache because it gets evicted by space and memory. So having something like this KV cache pool that we can sort of offload from local device memory allows us to get much better prefix cache hit rates, kind of like I said, as those requests finish on these agentic workloads. So really cool. There's also this blog in collaboration with DigitalOcean, where they talked about how they use vLLM and the optimizations we've ultimately done together to optimize DeepSeek 3.2, Minimax M2.5, Qwen 3.5, the largest one that's open source. And yeah, kudos to them for making it to the top of the artificial analysis leaderboard. But also kudos to us for vLLM having the performance to get to that state-of-the-art level. And of course, sharing all those improvements with the community in code, but also in sort of explanations and diagrams and walking you through the rationale behind those performance things. So yeah, if you're interested in like frontier model performance, what that takes, this is a great blog on that. Next, there's a blog from one of our researchers actually here at Red Hat, Eldar Kurtik. I helped a little bit on this, so I'm a bit biased, but you've probably heard a lot about TurboQuant, the like Google KV cache compression paper. Ignoring the research controversies around it, we have landed some related implementation to it inside vLLM, and it's been there for quite a few weeks now, with different levels of compression, yeah, there's a sort of we found that there's sort of a lot of misinformation or like over justification, I guess, of like how or like exaggeration of how good the method is. And so we wanted to compare it against the sort of well supported FP8 KV cache quantization and attention quantization that we've supported for much longer in vLLM. And essentially there's some performance benchmarks in here at load that show TurboQuant is basically going to give you not really an improvement on token speed. It's pretty much always going to be a bit slower because you're paying that extra cost to compress and decompress, but it can certainly like give you more KV cache capacity fitted on capacity constrained GPUs. But certainly if you're running like models at like production scale on data center GPUs, FP8 KV cache is like a really good middle ground. And I think the thing that's especially left behind in a lot of the conversation is like proper accuracy evaluations on sort of standard industry standard benchmarks, like reasoning evaluations like GPQA Diamond or Math 500. And there's some interesting results there that really show some of the more aggressive types of turbo quantization, like down to 3-bit or 4-bit, actually can hurt accuracy quite a bit. And so the people claiming that it's lossless, we need to temper their expectations a bit and ultimately aim for higher standards and in terms of like harder benchmarks and accuracy evaluations. The same way we talk about model quantization, we should bring the same thing to KV cache quantization. So yeah, recommend checking it out. And next, I mentioned vLLM Omni before, which is a omni-modality extension of vLLM, ultimately focused on multimodal output models as well as multimodal input, which vLLM supports natively. And yeah, there was a great announcement in combination with vRL, which is a very popular reinforcement learning library that uses vLLM. And this is, talking about the co-development that went there in order to build, an RL stack for omni-modality models, using, vLLM Omni, of course, and building a new sort of vRL Omni integration. So yeah, you can get started on the latest omni modality or even multimodal output models for reinforcement learning, which is really cool, and recommend trying out some of the examples that they walk through in the blog. And last, in terms of blogs, we had a sort of announcement of like the elastic expert parallelism support in vLLM that's been in development for a while. This has been, really important for improving the sort of fault tolerant serving for wide expert parallel deployments of vLLM. Ultimately, expert parallelism is interesting and requires this kind of flexibility because expert parallelism allows you to scale your single deployments of large frontier MOE models like DeepSeek much further than just one node of GPUs. You can run like a expert parallel 64 or 96 deployment. So running like DeepSeek 3.2 across like 64 H100s and serving 10,000 concurrent requests while still getting like a decent per user latency, but like able to get a lot more token efficiency and thus make more as an operator of the API of the model. But as you scale one model deployment on more hardware accelerators, you ultimately run into hardware accelerators failing more often. Or certainly, inefficiencies of that very expensive deployment you have maybe not needing to be so large at night when maybe your workload goes down by half or a quarter. So Elastic EP is exactly like that. It allows us to dynamically change the amount of parallelism of a live running deployment, resharding experts across GPUs dynamically as GPUs or nodes fail at runtime, and we want to recover and not have the whole system crash and need to deal with startup costs. And of course, scale the number of GPUs that are running that workload dynamically up and down as your workload distribution changes over time. So yeah, obviously a really important feature for production deployments of state-of-the-art models. So yeah, great to share this, and I think the UX is quite nice. So yeah, those are the updates in terms of blogs. Now I'm going to cover what's new in the latest vLLM release, 0.21. It was a pretty sizable release, 367 commits from over 200 contributors, 49 of those new. So congrats to them. In terms of breaking changes, the two things that I'd really call out is transformers less than version 5 has been officially deprecated. We fully migrated over to transformers 5. This is a great improvement for most models. There's a few models that still have some bugs, but those are ultimately pretty old models or not commonly used. So we feel pretty good there, but please let us know if you run into blockers. Slight update for building. C++ 20 is now the default for building. This is something we can't control too much and needed for PyTorch support, but still want to call it out regardless. Yeah, we had quite a few model releases within this release window. So the latest Nemo v2.5 model, Moondream 3 support was added, which has been in works for a while. The latest Cohere model released, and the Laguna model from Poolside AI released as well. DeepSeek v4 saw support for AMD ROCm GPUs finally landing, as well as pipeline parallelism support. And we have a lot more optimization work incoming for v4 that's on the way in the next release. And yeah, we've been improving spec decoding compatibility with reasoning models, making it work better with reasoning parsers, and yeah, like thinking budgets and things like that, and generally improving the amount of MTP modules we support natively as speculators that ship with models on release, like Gemma 4. Yeah, ongoing development on Model Runner v2. It's still only enabled by default for like a very few number of models, but stay tuned for as we start using it more and more. In terms of quantization, we added initial support for MVFP4 KV cache on NVIDIA Blackwell GPUs through the flashing for attention kernel. This is pretty cool. Where we still have like some development on there to get the sort of accuracy performance trade-off right. But I think it could be pretty interesting and eventually with kind of much better than TurboQuant in terms of the hardware support and acceleration available with like FP8 attention and things like that. Yeah, several like fixes related to Gemma models. In terms of LoRa, we finally added initial expert parallelism support. So before, if you wanted LoRa on MOE models, you were sort of restricted to tensor parallelism. Now expert parallelism is supported, which should be great, especially if we eventually scale up to elastic expert parallelism. Yeah, and a lot of work in terms of KV offloading and the hybrid memory allocator. We're sort of undergoing a bit of a refactor there and working on how we want to, ultimately build the most performant KV offloading as we see vLLM used in more of these, agentic workloads that require, long-term KV cache management and offloading at hierarchical levels of memory on the GPU, memory on the CPU, and long-term storage on device. vLLM was a part of the XGrammar 0.2 release, and there was a cool blog there on a lot of the new features in terms of enforcing structured outputs while the model is doing generating tool calls or reasoning. We expect this to be a really important feature to improve the success rate of models making tool calls in the future. The Kimi team has, or the Moonshot AI team, had posted this like Kimi vendor verifier benchmark several months ago. And one of the key things to meeting the like reference tool calling accuracy that they look for in production is exactly this of enforcing the model so that when it's in the middle of generating a tool call, we actually restrict what tokens it can choose to only tokens that are valid as like a parsable tool call. So yeah, we are landed the initial support for sort of general support, I guess, for models, and are working on expanding it on a model by model basis. Yeah. Some API enhancements, responses API, better improvements in robustness with streaming tool calls, some RLHF, weight update API updates. We finally were able to re-enable the optimized flash infer top K top P sampler. So if you use those sampling strategies, should be a lot more improved. Yeah, we've been squashing a lot of GPU CPU syncs in the model runner. We actually have like a specific PR for a CI job to cache these things more often, as asynchronous scheduling is really important nowadays. We added a new optimized MLA backend for MLA attention models like DeepSeek or Kimi, optimized for Blackwell thanks to the Token Speed project. I've been expanding like FP8 attention and MOE support on CPU, adding LoRa to XPU. We managed to make the Docker image even smaller by squishing some intermediate layers. We still have a bit more to go. I think it's around like 10 gigabytes on the official one compressed. Up from like 20 gigabytes like a few months ago. So it's at least a lot better now. And we've also been working on lowering the many Linux requirement for the wheels, as this unfortunately jumped up for CUDA 13 a while ago for the bump to match PyTorch on the latest release. That was a long spiel of things, but that's all I'm going to cover here in terms of the release. Happy to cover more in questions afterwards, but for now I'll hand it off to Christoph to talk about Intel CPUs on vLLM.
Okay, let me just take over the screen. Hello, I'm Krzysztof Wiśniewski. I'm a software engineer at Intel. Previously, I've been working at contributing to vLLM support for Intel Gaudi, but right now I'm supporting AI customers. And today I want to show you how to work with Intel CPUs on vLLM. So we'll go through supported use cases. I will also talk a little bit about CPU resource management because it is very important. Additionally, I want to show you how to run it in production because running it on Kubernetes is very different than running it in Docker. Then I will show you how to properly scale it. And after that, we'll have a little time for Q&A. So here you see the matrix of what we are supporting for online cases. please treat it as a rule of thumb because it will vary very much on the model that you are running, the hardware you are running, and on many other cases. But we are supporting Q&A, quick Q&A, code generation, content enhancement, and long documents. So basically, we are telling that we are supporting up to 4K context length in this case. But I will go through that a little bit in more detail in the next slide. So here you have more detailed display. On Xeon, SLMs works very good. Also, more models where a small amount of active parameters is running at the same time are good. Also, long context workload, when you don't need response immediately, is currently very good for Xeon because as the RAM prices are rising, the RAM on Xeon is much cheaper, and we can fit much more context in that case. In the moderate concurrency servers, it is also fine. We are also supporting reasoning models where latency is flexible. And since when you are running a GPU or an accelerator, you still need CPU, it is much more cost effective to run it on CPU. We do not position Xeon for high query per second consumer chats or where we need very tight time to first token SLAs or when we want to scale for many thousands for users. So in the short terms, it is best to run MOE models, small models, and that's all. So with that, I want to show you what you might expect from the Xeon with Xeon AI Performance Advisor, which was introduced last week. This is a web-based interface that, based on your requirements for the model, will calculate you how much resources you will need and what is the estimated cost of that and what performance you will get. So with that, let me show you the XPA itself. Here you have support for CSPs and on-prem deployments. Let's go to the CSPs because that is the easiest to reproduce. You see the same screen as previously with the recommendation. So let's start with the case that maybe you need some chatbot for your page that will have very easy questions. So for example, you will want to just get the information of the order on your shop. So let's assume that you need quick QA. Since it is designed for customers that might not necessarily know how many concurrent users you will need, because maybe they are business people and they don't need to know nitty-gritty of amount of users. So you will tell it that calculate that for me. And let's say that you are expecting 300 users at the same time. Let's choose the SLA that you want to have. So this is an example, it's production deployment, so which is SLA guaranteed, and it will tell you that your highest concurrency level will be about 45. Or because we know what concurrency levels are, we can just type in 50 and it will show you what hardware you will need for 50 users. In that case, we can also select the model size. Right now for CSP deployments, we only have 8B models, and we also can choose the quantization since Xeon is supporting BF16, Int8, and Int4. And after that, you will get what hardware you are supposed to get and what performance to expect. So in that case, it told us that you have SLA for time to first token about 3 seconds. For time per output token, you have 100 milliseconds, so you are guaranteed to get under that. And you have three deployments. So first one is optimized for TCO. So we are trying to get as much from our hardware as we can, but we don't necessarily need the fastest response. So in that case, you'll have time per output token about 100 seconds and time to first token about 3 seconds, but you only need on AWS R8i 8x large, which will per year cost you about $40,000, so it's pretty cheap. So also you have balanced, where you are getting R8i 40x large, 3 instances of that. This is much more expensive, but you are getting much better TPOT and much better time to first token. And of course, if you want to reproduce those results, you can also do that. Here you have example. Here you have how this test was run as a server command, how it was run, and how it was stressed with vLLM bench. Don't worry about those parameters. We also have page where you have optimized parameters for all other models. And also below that, you have just pure data from the benchmarks, what was measured. And this not necessarily is recommendation. This is just a pure data if you want to go into that. So going back to the presentation, we also have AI software catalog, and this is our entry point for all the AI solutions for Xeon. So if you want to see what you can do with it, you have already ready to deploy production grade solutions. Also, you have models which are supported with all the details how to get it running. We are aiming to have NGC and NIM-like catalog. And going into that, you just go into softwarecatalog.intel.com. And in that, you have this page. Here you have models. So here's the part of the models that we are supporting. If you go into model, you can, let's take as an example, Gemma 4. In that, you have overview of the model. Basically, it's very similar to what you will see on Hugging Face. You have on which vLLM version it was tested, with the image itself if you want to give it a try. And you have deployment, which is just pure commands that you need to pass and get it running. Some example comment to see if it is working. And additionally, you have Docker Compose for that and how to start it. Except that we have solutions here, which are just to inspire you what you can do with this vLLM on CPU. So for example, here we have ChatQA, which is enterprise grade RAG, which is running purely on CPU without any accelerators. If you look at it, you have full guide how to run it. So step-by-step instruction. Maybe you have existing Kubernetes cluster. Maybe you have a new cluster. It will also show you how to deploy Kubernetes cluster. And if you go through all of those steps, you'll have running cluster. And here you can see what the performance you'll be expecting in that cluster, depending on the model that you are running. There should be also explained on which hardware it was run and how it was done. Basically, all of that is reproducible. You can do it by yourself. And going back to presentation, we have those solutions that I've shown you, the models, and also we have the second model list, which was validated but not yet put into software catalog. We have, as you can see, the dense models, so Llama family, Qwen family, Gemma, Gemma Dense 5.4, Granite, but also we have some models that are voice to text, so Whisper is here. All of those dense models are supported in BF16 format, int4, int8, but you can also run it in AWQ, which we'll be using int4. We also are supporting a mixture of expert models. So Llama is here, Qwen3 is here, and here. And with that, I need to explain one concept about running it on CPU, because it is a little bit different from accelerators and GPU from this core pinning perspective. So, but first I need to explain what NUMA node is. So NUMA stands for non-uniform memory access. This means that you have regions on CPU which don't have the same memory bandwidth as other regions. So for example, you can have one node with two separate CPUs, and in that case you have NUMA, two NUMA nodes, because they have separate memory and time to access from first socket to second memory will be higher than from first socket's memory to first CPU. Historically, it was that NUMA node was whole CPU, but with recent introduction of sub-NUMA clustering, you also have chiplets that are parts of CPU. So if you have SNC enabled on Granite Rapids, which is newest CPU generation, you can have on a single physical CPU 2 or 3 NUMA nodes. And why is that important for running vLLM? Because you can imagine that the example that if you have GPU and you have part of weights on one card, and you will be trying to access it from the second GPU, it will hurt the latency, and we don't want to have that situation in case of CPU. So that's why we need to explicitly say to vLLM or container that is running vLLM that, hey, you can only access those cores, and it will be accessing only memory from that belongs to it. By default, what vLLM is doing is registering one rank as single node. So if you will be running Tensor Parallel 2, it will take 2 NUMA nodes from you. This is good in Docker, where you have access to all the cores. And you can also specify which cores it is running via CPU set CPUs parameter. But when you go into production with it and go into Kubernetes, there are bigger issues. So in that case, you are not, when you are requesting some amount of CPU in Kubernetes, you are not telling it, hey, give me, for example, 16 cores. You are telling him to allocate for you time of 16 cores. So for request, it will be what is guaranteed for you. And for limits, is what the process can take at the max. So basically what vLLM sees when it is starting, it is seeing that, hey, I have available 64 cores. So I'll be scheduling 64 threads. But if you specified in request and limit 16 vCPUs, that is not true, because it has only CPU time for 16. So basically it will, all the threads will be running 1/4 of the time that it has allocated. And this will lead to very significant performance drop. So it is, when you are running on CPU, it is very important to allocate those cores properly. And what is our solution for that? So if you're an advanced user and you want to play with it a little bit, you can use NRI's resource policy balance. So basically in Kubernetes, you are specifying how many, by the container name, how many resources you want to allocate to that. And it will ensure you that you will have those cores available for you. You can also specify here that you want to have exclusive cores. You also can specify that if you have hyperthreading enabled, not to allocate or to allocate those hyperthreads. And it is, you need a little bit knowledge to use it, but in the return, you'll have very good results. And in example, when I showed you the ChatQA example, this is what we are using. So if you, in that case, we are trying to saturate the platform efficiently. So when you have hyperthread, there are services scheduled on the same hyperthreads because they are very lightweight and they don't need their separate cores. So in that case, you can efficiently use them. Also, we have a whole solution for that. We have Intel AI for enterprise inference. So it will automatically ping the cores for you. Also, this is a whole enterprise grade solution. So with that, you have authorization. It will deploy vLLM for you, everything that you need to run vLLM on Kubernetes. Additionally, you can play with Kubernetes settings. So if you properly tune kubelet, you will set CPU manager policy to static and add additional parameters to topology manager. So you'll tell him to allocate whole CPUs. You will get similar result. But the trade-off is that when you have hyperthreading enabled, so you'll have 2 threads per core, you have to allocate the both hyperthreads to the same process. And that will result that you cannot put anything other on those same cores. Okay, so now I want to quickly go through the scaling. So as a starting point, I will recommend you to just use one NUMA node as one rank. If you want, you can play with that, but starting point, this is the best starting point that I can recommend. So then you will need to tune the latency of this one rank. And if you see that your responses are too late, you just go with another rank with tensor parallelism. And if its latency is fine for you, you can just scale, add another replica, or use data parallelism for another rank. Also, we are supporting embedding in the ranking since those tasks are much lighter than going whole through model. You should be allocating only 4 physical cores per replica as a starting point, because running it on the whole NUMA node won't give you the best results. At least that's what we found in that chat Q&A case. So what I want to remember from the presentation is that you can try running AI workloads on CPU. It will work with vLLM. We are trying very much to have it as good as possible. You can find our hardware in any of CSPs, so AWS, Azure, or Google Cloud. It's available here. But when you are looking for Xeon, please look for 4th gen on newer, because here we have Intel AMX, which is instruction set for which is using tiles as a base registers, not only vectors or single register, which makes it much faster for inference. And if you want to start your journey with Xeon, here's QR code to software catalog. It is our main entry point when you can find all the resources that you need. And also, if you need, there's on the top right, there's a button to ask any questions. And also, I'm available on Slack for any questions, but if you have some right now, I'll be happy to answer them.
Awesome. Thanks a lot for covering that. One question I saw in the chat was like what are the targeted token sequence lengths for use cases on Intel CPU? Yeah, is it prefill around 4K tokens or total prefill decode? I think they're just curious about.
Okay,
Yeah.
so
Yeah.
this slide that I've shown that it was showing the 4K, it is recommended for only online cases that will improve in future. But as a rule of thumb, this is about 2K for prefill, 2K for decode. You can. There are some cases that we found that more of that is working. So, for example, we were trying with text summarization, and it was working fine. But this is just a rule of thumb.
Yeah. Okay. Yeah, totally understood. Are there yeah, some other questions people want to post in the chat, or feel free to come off mute and ask directly to yeah, one question I had was like you showed like a pretty broad list of models and like your validated model list. I was curious if there's like yeah, any like architectures that you could say are like, you know, prioritized next, or like yeah, or like key target.
So for the future, I don't know. From it's I don't have any roadmap as of today.
Okay, sure. Yeah. Yeah, one thing was I think you kind of like talked briefly about, you know, like the scaling strategy, but I'm curious if you have like some yeah, like concrete examples of like yeah, deployments of like yeah, tensor parallelism on like or like multi-node CPU inference. Like I kind of don't know enough myself, so I'm a bit curious where it could be good.
So for tensor parallelism, let me just show you again this XPA. So with tensor parallelism, we have also in XPA the on-prem setup where we have much bigger nodes. And if you go, for example, into content generation, let me show, for example, 50 users. Here we will have setups that are using multiple tensor parallel ranks. So basically, we'll have per one NUMA node scheduled one rank. In terms of multi-node, so as you can see probably here, it will be showing, yeah, this is tensor parallel size where I would need to look up what the CPU model is, but each of the rank will be one NUMA node.
Okay, cool. Yeah.
In terms of multi-node, what we are recommending is just having multiple vLLM instances.
Okay, yeah, I see. So like horizontal scaling.
Yeah, exactly.
Yeah, replica scaling. Okay, cool. No, thanks a lot. Yeah, this calculator is pretty cool. I like this performance advisor. Yeah, question from Yang. High bandwidth and memory efficiency have been the focus of vLLM. Are there any thought on optimization for low latency? We're definitely, I think, focused on yeah, also if you could share the perf advisor link. Yeah, someone just asked for it.
Yeah, of course. It is in presentation. I'll also type that into the chat.
Cool. Yeah. So yeah, we are definitely you know, focusing on low latency, you know, low batch size cases a lot more. Particularly, I would say like still like long context length, right? But as you go into like serving requests with like, you know, 100K tokens for each context, you sort of aren't able to get like the same like very high batch size. So there's a lot more focus on sort of like, yeah, you know, 16 user concurrency, 32 user concurrency, meaning that's like how many requests are like actively running, at least for like aggregated deployments. And yeah, so there's a lot sort of different kernels that you want to write certainly from the like GPU perspective, where you maybe don't even want to use tensor cores for some operations that you would before. You want to keep it all in vector units, or yeah, certainly like fuse kernels together. So yeah, I would say kind of that blog I shared earlier about like vLLM and artificial analysis with DigitalOcean. There's some good deep dives there into like what's actually good for those particularly like small batch size inference, and there's a lot of other things, but yeah, active work. Yeah, there's a question from Afir. Is there demand for running LLMs on CPU? I think yeah. I definitely hear it from customers. There's a lot of CPUs out there that especially for I think like small language models, like as we went over here. There's like a lot of places where keeping it on device, or like very local, or just CPUs can be in different places than GPUs in the data center. Yeah, there's like some cases where it can be like even better latency and interactivity.
Yeah, let me add a little bit on that. So in some cases, you don't necessarily need GPU because you are not running that much of an users. Because if you look at the concurrency level in vLLM, not necessarily corresponds to how many users you are handling. Because if you have some chatbot, all the users that, for example, you have in organization are not running at the same time. And that's why when we in the Xeon Performance Advisor, we have this calculation. So if you type in that you have 300 users, it will show you that you need concurrency level, for example, of 50.
Yeah. And then there's one question from Venkata. Does Intel Xeon AMX support FP8? I'm pretty sure it has for a while. Yeah.
I think so too. I'm not 100% sure, but the models itself are supported in FP8.
Yeah, there's a few different generations of it, so
yeah,
hard to keep track, but yeah, it's definitely. I know Int8 has been well supported for a long time. Yeah, I need to check the.
Yeah, but the best performance I think that you will see from Int8 quantization. So from what I've seen, going from BF16 to W8A8 gives you much more performance.
Yeah. Okay. Cool. Yeah. Any other questions from people? You mentioned that MOE with few active parameters is a good use case for Xeon. Do you have any data on how that works with higher concurrency?
I think that if you go into Xeon Performance Advisor, a Performance Advisor on CSP, there should be more some data from MOE models. I'm not 100% sure on that. I will need to check that. But if you want, I can look up if we have some data on that. If not, it will be coming in the future.
Okay. Yeah. Well, I think that leaves us at a pretty good level. Yeah, I want to thank you a bunch for our special guest and covering a lot of interesting detail on Intel developments on vLLM. And thanks everyone for sticking along for the ride with all the updates from vLLM generally. Yeah, Sasha, do you want to round us off on what's next?
Yeah, see you in 2 weeks for the speculators update. 2 weeks after that for semantic router. We hope to see you in London or in Istanbul. We are planning many more meetups. We just don't have them booked yet. But if you have friends and colleagues in either London or Istanbul, please send them that invite. And you can always find us, and I keep pushing the vLLM Slack, but it's a great place to get direct access to me, to Michael, to Christoph, I believe. Sorry to send people your way, but that's an easy way to ask any follow-up questions in the vLLM Slack. It's slack.vllm.ai if you're not already in there. And since you're joining, if you do join our office hours channel where we share all of the exciting updates. Cool. Thank you guys so much. Really appreciate it. Christoph, you enjoy your day off tomorrow. Michael, I'll see you around, and everybody else, see you